मेरी my voice is audible. Okay,
हाँ हाँ,
so
आ रही।
I'm very thankful to Nikhil for making the necessary arrangement for the talk, and to Harsh for helping me with the corrections in the slide. I'm thankful to all of you for the participation especially to students who are to people who may have some time lag. Initially, I saw Ishbhaiya to be taking part to be a participant in the talk, despite of the time lag between India and America. I hope to make the talk interactive. Feel free to ask questions and interrupt me if there is some technical issue. Uh, so the title of my talk is Black Holes Information Paradox and Recent Proposals to Resolve it. So the overview of my talk is I will go briefly through Einstein's theory of general relativity. I will briefly describe black holes, which are solutions to Einstein's gravity, and how they seem to possess some similarity with the laws of thermodynamics. And if you include black holes to be part of some kind of thermodynamical system, we find that it's in trouble with the second law of thermodynamics. Uh, Hawking effect, interestingly, tries to rescue the above situation, but it uh, gives trouble with quantum mechanics. Uh, I will then go briefly through the newer versions of the information paradox and what are some of the possible ideas which seem to resolve the information paradox. Okay, so uh, what is Einstein's theory of gravity? As we all know, that Einstein's theory generalizes the Newtonian theory by assuming a space-time to be a manifold, and it's the interplay between space-time and matter which describes Einstein's theory of gravity. Uh, it is summarized beautifully through Einstein's equation, uh, r mu nu minus r by 2 g mu nu is equal to t mu nu. Uh, so the left hand side is a purely geometrical part, and right hand side is contribution to the matter field. So if so we can summarize beautifully in words of Wheeler that matter curves space-time and space-time tells matter how to move. So there are test objects which move in the space-time due to the curvature and follow shortest path or geodesics. And in turn, the matter field curves space-time which decides the path or geodesics in curved space. So uh, my voice is audible, no?
Yes, 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 yes.
Yeah, it's audible. Hmm.
Okay, so interestingly, one of the fascinating solutions to Einstein gravity is are black holes. So Einstein equations are coupled nonlinear differential equations, which are difficult to solve. However, when Einstein proposed his theory in 1915, uh, in 1916, Carl Schwarzschild uh, found a special class of solution to Einstein equation, which were solutions to vacuum. So it's space-time with no matter fields, and it describes a spherically symmetric solution, which we famously know as the Schwarzschild solution to Einstein equation, metric given as a, with the metric given in this form. Okay, the solution has now some interesting feature about this solution is that it has symmetry along the time and the component because the metric is independent of time. I don't know why the slides are moving naturally. Uh, so since it has no time or it has no GPT or G55 component, the equations are much simpler to solve. And the interesting feature about this solution is that it has a singularity at r is equal to 0, which suggests that at some scale, some I cannot directly argue that it's some high energy scale, but at some energy scale, the theory seems to be breaking down. Now, the motivation of my talk was to give a slight detour from what is general theory of relativity and consider its similarity with the laws of thermodynamics and how it led to the information paradox. So, the development in the Einstein's theory of gravity uh, got saturated for a long time after its proposal in 1916 because these were nonlinear differential equations which were difficult to solve, and the only solution which was found up in 1916 up till 1960s was the spherically symmetric solution, which was the Schwarzschild solution. However, a rapid development followed after the 1960s, where uh, many other classes of solutions to Einstein's equation were found. Uh, and subsequently, in 1970s, there were strong foundations which led to the formulation of laws of black hole mechanics. So, laws of black hole mechanics are four set of laws that any black hole spacetime seems to follow for Einstein's gravity. So the interesting feature about these laws are that they have similarity with the laws of thermodynamics. So just as we have the zeroth law for thermodynamics, there is an analogous zeroth law for black hole mechanics, which states that the surface gravity for any black hole is constant. Uh, just let me know if you have any queries in between, if you want to ask some questions regarding the presentation. Uh, so it it seems a bit difficult if you don't interact much. Yeah. So surface gravity is. I need to tell you how it's defined. So for black hole spacetime. So as the word seems to suggest, it's the gravitational force experienced by a test object at the surface of any astronomical or a gravitational object. Uh, Now, there are some troubles with how we need to define surface gravity for black hole spacetime because the gravitational pull at the surface of a black hole is infinite. But however, we can still so there are some techniques how we can modify the definition of surface gravity for black hole spacetimes. And interestingly, it's found that the surface gravity is constant for black hole spacetime, even for rotating black holes where there isn't symmetry along the phi component. So uh, the second law is analogous to the second law of thermodynamics. It states that the infinitesimal change in the mass of a black hole is equal to the infinitesimal change in its angular momentum uh, with as some multiplying factor omega and infinitesimal change in its area. The second law of black hole mechanics, which is also famously known as the Hawking's area theorem, tells us that the area of that no matter which kind of gravitating process you consider, the change in area always increases with time, which is similar to the statement that entropy of a thermodynamic system seems to increase with time. The third law is that surface gravity of any black hole spacetime is greater than zero, which is analogous to the statement that temperature of any thermodynamic system is greater than zero. So as of now, it seems just like a mathematical analogy rather than being something physical. So there are many reasons why one cannot make a precise relation between laws of black hole mechanics and laws of thermo, meaning one cannot assume that black holes are thermodynamical objects. Uh, uh, one reason one reason for that is that black holes, if you assume black holes to be classical objects, they do not seem to carry any entropy or temperature. I will go through these arguments as we proceed along. Now, along with the four set of laws of black hole mechanics, there was the famous no-here theorem proposed by Werner Israel in 1978, which suggests that black holes seem to carry another special property. So, suppose we have some gravitating object like a star. Uh, to describe it uniquely, one needs a number of properties like its mass, luminosity, its internal composition, like whether it's made of hydrogen, helium, its area, intensity, frequency, angular momentum, its charge, and so on. However, to describe a black hole uniquely, you only need three set of parameters: its mass, its charge, and angular momentum. So it seems like, unlike other astronomical objects like star, black holes do not seem to carry any hair, uh, which which has strong implications for information paradox, as we will see. Okay, so the no here theorem leads to the loss of entropy. So suppose we have a black hole spacetime. The no here theorem suggests that black holes are described uniquely by its mass, charge, and angular momentum. Now, as you all know, that entropy is a common measure of the amount of ignorance.
Bhaiya,
Uh-huh.
Rahul is asking, what do you exactly mean by here in this context?
Yeah, so no here means that, suppose you have a gravitating object like a star. It has some degrees of freedom, which we call hairs. And by degrees of freedom, mean you have some intrinsic properties of the star, like what it's made of, its intensity, frequency, and its luminosity. Meaning you can question quantum mechanically what's the composition of star. You can, but for a black hole, it's described uniquely by its uh, three set of parameters: its mass, charge, and angular momentum. So it seems like you don't need to know about its radius or its intensity to describe a black hole. Does that answer the question? Uh,
Yes, I think. Yeah.
yes. Thank you. So if you assume no here theorem, then it seems like, okay, so black holes seem to only carry three parameters to describe them uniquely. Now, as you all know, that entropy is a common measure of ignorance or disorder in a system. So, entropy of a thermodynamical system is described by the Boltzmann equation. S is equal to K ln W, where W is the ignorance in the system. But since black holes are described uniquely by its three charges, there is no ignorance about the properties of black hole. So it seems like, from the definition of Boltzmann, black holes do not seem to carry any entropy. Uh, is this statement clear?
Yes.
Yeah. Okay, so now this leads to an interesting puzzle. So John Wheeler asked his student Bekenstein, suppose one throws in a cup of coffee inside a black hole. Now, after a certain time, it collapses inside the black hole and becomes a part of it. So now, since black hole is described uniquely by its three charges and do not seem to carry any entropy, it seems that the entropy carried by the cup of tea is lost. Now, this seems to be in apparent violation with the second law of thermodynamics. Now, as you all know, that the entropy of all thermodynamical processes seem to increase with time, but this process seems to suggest that, in this case, the entropy of the system is getting reduced. Okay, so Bekenstein gave a very nice proposal for this inconsistency. He argued that black holes do carry entropy and behave like thermal objects. And he proposed that black hole entropy is proportional to area. There were two reasons why he did so. Now, as you all know, that horizon is a one-way surface. It hides information about the inside of a black hole. So an outside observer doesn't know what's the interior of a black hole, and hence, since it seems to hide information, it seems to carry entropy. And as we had discussed previously, that the second law of black hole mechanics suggests that for all gravitating processes, the area seems to increase. So it seems like the area of a black hole is in some sense analogous to the entropy we associate to thermodynamical objects. Please let me know if there is any doubt in if there is any doubt so far. Okay, so I should go on.
Yeah, continue.
Yeah, go on, Bhaiya.
Yeah, yeah. So this result had to be awaited soon to be confirmed by the famous discovery of Hawking, which we all know as Hawking effect or the information paradox. So before describing what is information paradox, am I will try to present some properties of black body radiation, which will be essential in understanding the Hawking's information paradox. So we know that black body radiation is an electromagnetic radiation emitted by hot objects when the objects are in thermal equilibrium with the surroundings. And these objects follow the black body radiation curve, which is shown in the graph. So initially, the you can see the graph here. The left, you can assume the left hand side to be the variation of intensity versus the wavelength. So at zero wavelength, the intensity of radiation emitted by electromagnetic object is, I don't know why it's getting, the radiation emitted by electromagnetic object is almost negligible. And at some particular wavelength, the intensity peaks up and then it falls down eventually. And the spectrum is different for different stars. Uh, we don't need to get an explicit detail of how the spectrum changes with the variation of temperature. What we essentially need to know is that the radiation of black body is homogeneous and isotropic and is universal for all objects. What I mean by that, two different thermodynamical objects. Uh, by different, I mean two objects which differ by observing them. So suppose you have an ideal gas system and a system of say van der Waal gas. If the two systems are at same temperature, the radiation emitted by them would be a black body radiation and would be homogeneous and isotropic. It will be universal and wouldn't seem to carry information about the nature of the object. And as we know that the mean number of particles emitted by the black body at some energy E follows Bose-Einstein statistics. Now, one may question that the black body radiation seems to hide information about the constituents building it up, because the outgoing radiation seems to not carry any information about the constituents making it up. But it doesn't, and it seems that since we are not able to uniquely define the quantum properties of the system, it seems to be inconsistent with principles of quantum mechanics. But if you measure the uh, properties of each single atom which is radiated as the black body, you will find that can uh, you can figure out what are the properties of the internal composition of the system by studying the properties of large number of atoms or radiation which is emitted out as black body radiation. But the composite system seems to follow the Bose-Einstein or the universal statistics. So it isn't that black body radiation seems to give any paradox with quantum mechanics. Now we'll find that there is something different for Hawking radiation as we go along. So the okay, so we had Bekenstein had proposed a framework for the proposal. Bekenstein had given a framework that black holes should behave like thermodynamical objects and should carry entropy. Uh, there were a number of reasons why Hawking. So I can't go exactly through the number of reasons which Hawking had in his mind to do the calculation of to do find the spectrum of radiation emitted by a black body. Uh, I can just tell you that he assumed the framework to be semi-classical gravity. So, what does semi-classical gravity mean? We know that Einstein gravity is a classical theory. It and we do not have a well-defined, precise theory of gravity. At least not in the 1970s when Hawking did his calculation. So one assumes that properties like the metric in the spacetime are classical and assumes quantum field to be propagating in the classical spacetime. So the left hand side of the Einstein equation, r mu nu minus r by 2 g mu nu remains the same. However, the right hand side, which is the stress energy tensor, which carries contribution from matter field, is now quantum because we are assuming the propagating fields in the spacetime to be quantum. So, uh, T mu nu, the stress energy tensor, is now promoted to an operator, and we take its expectation value with respect to some state psi, and we equate the two sides, and this is called the semi-classical gravity. So this is the framework in which Hawking considered his calculation for the black for the Hawking radiation. Okay, so now you may question about the validity of semi-classical gravity. Since it's not a complete theory of gravity, any result which it would seem to give may not be entirely consistent with the may not be entirely consistent or may lead us to paradox because it's not a complete theory. So the scale in which semi-classical gravity is valid is the Length scale much greater than the Planck scale LP, so that quantum effects can be ignored. And I will let you know about what are back reaction effects later. So it's assumed that back reaction effect can be ignored, and it's in this limit where Professor Hawking found his famous information paradox. Okay, so I'm now considering a very brief review of what Hawking effect is. So Hawking, so are you all familiar with the Penrose diagram?
No, just explain what a Penrose diagram is.
Yeah. So uh, to study the so suppose you want to study the dynamics of any gravitational process. Penrose diagram helps to simplify the picture by giving a pictorial view of the process by representing it in two-dimensional space. So suppose you have a very large space-time. Now you can always do some coordinate transformation such that the space-time shrinks to a very small region. So as an example, suppose you have, you know that tan x uh, at x is equal to pi by 2 goes to infinity. But you can always do a coordinate transformation. Uh, y is equal to say tan inverse of tan x. So meaning you can shift from some function tan x to x, which is finite in its domain. So what Penrose diagram tries to do is to compactify all of the space-time into some finite region. So the boundaries which you can see here, I plus is the future time like infinity. Small I plus is future null infinity. I is sorry future Okay, I'm getting a bit confused. Okay, so um, yeah, these boundaries are regions at infinity. So some region very close by in the Penrose diagram is infinitely far away from this point. And what Penrose diagram is eventually doing is taking the metric dA square is equal the Schwarzschild metric, which has four components, and compactifying the spherical coordinates, meaning you just ignore the spherical coordinates and just study the variation of the time part and the radial part in the Schwarzschild geometry. So is this clear?
I'm sorry. What do you mean by compactifying again?
Yeah, so you just remove away the spherical part of the metric. So it's just a planar diagram. So you have removed the spherical part of the metric. Uh, is it clear?
Yeah, just go ahead. Let's go.
Yeah, yeah. So suppose you have some matter fields in this spacetime. These matter fields tend to collapse and form a similarity at r is equal to 0, and event horizon at r equals 2gm. So that is the Penrose diagram. And what Hawking considers are quantum fields in this spacetime, in Schwarzschild spacetime. So these quantum fields are labeled by four set of coordinates, tr, theta, phi, and you you can choose an action for the quantum field so that they satisfy the sorry where is so that they satisfy box of phi is equal to 0. Here box is the D'Alembertian. So you will find that the solution to this equation are the radial part of this solution is r omega l r star, and the spherical part is ylm theta phi. Now, since ylm theta phi is universal and is independent of r, we can just remove it up, and that gives us the Penrose diagram. So r star here are the coordinates outside the horizon of the black hole, and are given as r star equals r minus rs length r by rs minus 1. Here rs is the Schwarzschild radius 2gm. So these are the classical solutions to background fields in a Schwarzschild spacetime. Now, what one tries to do is to quantize these spacetimes, and one considers the limit when r star tends to infinity. So r star tends to infinity means that you are considering incoming waves from infinity. These waves go past the horizon, they get scattered. Some part of the wave goes to future infinity and some goes inside the horizon. Okay, is that clear?
Oh,
Huh?
yeah, I think so. Go ahead.
Okay. So given that uh, in the limit r star tending to infinity, you have the natural intuition that r omega l r star will have the plane wave solution, something like this. And since it's a plane wave solution, you can quantize the fields phi, assuming it to be free fields, as we do in quantum field theory. So phi P r theta phi in the limit r tending to infinity can be written as phi incoming wave, which can be written in the momentum space as as this integral with creation and annihilation operators ak and ak dagger. So you're getting the intuition for why I'm writing the creation and annihilation operators, because these are like free field waves. So you can always choose the basis component of phi t r theta phi in the momentum space to be like creation and annihilation operators of harmonic oscillators, since it's a free field. This point is clear, no? And
Yeah.
yeah, so we are assuming omega is equal to k for massless fluid. You all know the dispersion relation. Omega is equal to root k square plus m square. So m is 0 here, so omega is equal to k. So we can interchange. For simplicity, we'll write the creation and annihilation operators with the notation ak, and a dagger k is the Hermitian conjugate of this. Now, the fields since these are free fields, they follow this commutation relation. And if you use this Fourier transform equation, you will find that the creation and annihilation operators obey the equation for free field harmonic oscillators. And given these free field harmonic oscillators, one can define the vacuum state uh, zero past null infinity. Where is the arrow? Yeah. So zero. So this is the vacuum state with past null infinity, and this is some state which gets annihilated by the annihilation operator. Okay. So as we have written the incoming wave, we can also write the solution for the outgoing wave. Okay. So this is all the intuition for what I was trying to tell you. So I hope it's not required much. We can review it later if uh, it needs to be done. Meaning it was just to describe the same process using the control diagram, how we rewrote the fields. Now, just as we defined the incoming waves, we can define the outgoing waves. So these are waves which are going through the horizon. So these are the incoming waves, and so when this wave propagates to the horizon, some of the waves go inside the horizon, and some of the waves get scattered due to the potential at the horizon. So we call these waves outgoing waves, and the outgoing waves at r equals to m can be written in terms of creation and annihilation operators. So
शांश भैया
yeah, हाँ बोलो.
स्लाइड्स नहीं दिख रहा है अब आई थिंक जिस डिवाइस से यू वर प्रेजेंटिंग यू हैव लेफ्ट द मीटिंग विद दैट वन
नहीं मैंने ओके आई एम सॉरी.
ओके हाँ जस्ट स्टार्ट द प्रेजेंटेशन अगेन स्लाइड्स
या आई एम सॉरी. शुड आई मैं रिजॉइन क्लिक करूँ क्या?
नहीं नहीं, बस प्रेजेंटेशन दोबारा स्टार्ट कर लो नीचे.
ओके ओके या अब क्लियर आ रहा है. अब क्लियर आ रहा है.
नहीं नहीं नहीं.
अब अभी नहीं आ रहा है आप दो डिवाइस यूज कर रहे हो क्या लैपटॉप और फोन
हाँ फोन में पता नहीं ये कुछ मैसेज आया तो मैं वो हटा रहा था तो एक बार ये.
ओके 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 सो फोन पे स्लाइड्स चल रहा है क्या
क्या करूँ.
नहीं नहीं, लैपटॉप से दोबारा स्क्रीन प्रेजेंट कर लो. फोन से सिर्फ
लैपटॉप पे है
ऑडियो.
ना स्लाइड्स
हाँ
अच्छा
हाँ,
अच्छा
नहीं वो
कूल
स्लाइड्स लैपटॉप से ही हो रहा है, फोन सिर्फ ऑडियो के लिए किया बिकॉज ऑडियो नहीं हो रहा था.
कूल 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 तो वापस से प्रेजेंट कर लीजिए
अभी नहीं आ रहा है. ओके ओके मैं देखता हूँ. हाँ समझ गया. ओके तो मुझे वापस जाना पड़ेगा ना.
आई थिंक आपका लैपटॉप से डिस्कनेक्ट हो गया, लैपटॉप से रिजॉइन कर लो.
ओके या समझ गया. थैंक यू. यही है हॉटस्पॉट. ये थोड़े कम टाइम का है. सॉरी. अब क्लियर आ रहा है.
रिजॉइन नहीं हुआ अभी.
हाँ ओके या
रिजॉइन नहीं हुआ अभी.
आई एम सो वेरी सॉरी. ओके अब क्लियर आ रहा है.
एक काम करें स्लाइड्स तो हम सबके पास है हम में से कोई एक स्लाइड प्रेजेंट करता है आप एक्सप्लेन करते जाइए और आप चेंज
परेशान
कर क्या
नहीं आ रहा.
स्लाइड्स नहीं आ रहा है क्योंकि
Yeah.
Shreyansh, maybe rejoin, like leave the meeting and then rejoin and then try to present.
Yeah.
Sorry.
Uh,
हाँ I think अब present करें. No, I think it should work.
huh. Okay, so अब आ रहा है?
नहीं slides नहीं दिख रही. No, wait, I have opened it on my laptop. मैं present कर देता हूँ. आप बता देना जब slide change करना होगा. भैया हाँ
हम
अब हो
एक
गया
मिनट।
हो गया हो गया हो गया हो गया हो गया.
सॉरी। हाँ तो where was the connection lost? मतलब did you go through the commutation relation?
हाँ commutation हो गया.
Yes, right here, right here.
Also,
So we know.
one doubt. Like earlier you said that black holes like we characterize by charge as well. So like suppose like
Yeah.
जब हम interaction की बात करें तो in the Lagrangian we should also have some interaction term that we will incorporate while talking about.
So this is just the electromagnetic charge of the. I mean, black hole can be charged due to some reason. Meaning, there can be some object which gets thrown into the black hole and it supplies it with some charge. So
Okay.
I had to discuss any general black hole can have a mass charge and angular momentum. These are called Kerr-Newman black holes, which are the most general black holes in Einstein gravity. So does that answer your question?
Yeah, it's yeah.
Yeah. Okay. So we know what are the creation and annihilation operators, and we can define the vacuum state at past null infinity as the state which annihilates the vacuum, which gets annihilated by the annihilation operator. Now, just as we, sorry, just as we wrote the incoming wave, we can also consider the outgoing waves. So these are waves which tend to follow through the horizon of the black hole. So the outgoing waves would be waves which get scattered through the horizon of black hole. Some waves go into the interior and some go outside. So these are called the outgoing waves. Now you can assume that since the fields are massless, you can rewrite the outgoing waves as free waves in some eigenbasis. Uh, does this is this point clear? Meaning you can write the outgoing waves in terms of free wave packets.
Okay.
Okay. So you need two set of creation and annihilation operators. One set of annihilation and creation operators for modes which are going into the horizon, uh, which go into the horizon. And you also need another set of creation and annihilation operators for modes which are going to future time like infinity. So I've used four set of creation, four operators here, and they should satisfy this algebra since they are free field operators in some eigenbasis. Okay, so just as we defined the vacuum state at past null infinity. We can also define the vacuum state at the horizon, but also we aren't much bothered about those vacuum states. What we just want to know is that the annihilation operator Bk doesn't annihilate the state at the past null infinity. So as the incoming waves goes through the Schwarzschild spacetime, it seems to suggest that the vacuum state of the incoming wave has changed. So this is a feature of vacuum state in any quantum field theory, that it's not unique. So suppose we have two set of observers. One is both of the observers. Yes, I'm sorry. One observer is at rest and the other observer is accelerating. So the two observers would not agree on the definition of the vacuum state. Uh, I don't have a very immediate argument to justify this statement, but as in empty spacetime, the incoming wave passes from past null infinity to the horizon. They undergo sorry, they undergo stretching due to the spacetime curvature, which changes the initial vacuum state to an excited state. So the curvature of the spacetime supplies energy to the vacuum state, and it turns it into a different state or some excited state. The non-uniqueness of the vacuum state would be essential in the Hawking process. So yeah, can you give me a minute, please? I just wanted to drink water. Please let me know if it's clear, meaning if you have any doubt, please let me know. Okay, it's all fine, na?
Yeah, it's fine.
So given the incoming, since phi is a scalar field, we know that we can equate the incoming and the outgoing wave. And there must be some set of transformation which relate the incoming and the outgoing wave. These set of transformations are called Bogoliubov transformation. So if you consider the outgoing wave written in this form and equate it with the incoming wave written here, you can equate the creation and annihilation operators of the You can equate the creation and annihilation operators of the incoming wave with the outgoing waves. So these set of transformations which relate the incoming modes with the outgoing modes are called Bogoliubov transformation. So BK can be rewritten as a summation over in this form. So BK, the annihilation operator at the modes going into the horizon, is some linear combination of annihilation operators at the past and infinity with some both coefficients alpha and beta star. Uh, these coefficients in general are complex valued, and their exact form depends on the geometry of the spacetime. Okay, so
We can the Bogoliubov transformation also exists for the metrics, right? Like we can directly do a transformation in the metric.
yeah,
But
so that's to it, meaning I didn't give an explicit formula for how we compute the Bogoliubov transformation. But what you tend
Sorry,
to do
could
is,
you yeah, I'm sorry, could you repeat that? Like, what do you mean by Bogoliubov transformation of the metric?
so it's some set of transformation which relate to different vacuum states, the creation and annihilation operators of two different vacuum states. Now you can equate the incoming wave with the outgoing wave since it's a scalar field. So you can equate the creation and annihilation operators in the momentum space of the incoming wave with the outgoing wave. And when you equate that, you can find some relation between the coefficients Bk, Ck with the creation and annihilation operators Ak and Ak dagger. Uh, Now, the explicit dependence of Bk would depend on the geometry of the spacetime, but you can assume that there will be some coefficients which will relate different creation and annihilation operators. These are called the Bogoliubov transformation. I think that's clear.
I'm sorry. I believe I suppose Nikhil mentioned something saying that you can do a Bogoliubov transformation on the metric directly. That's
Yeah,
something
I
I did
mean,
not.
no, I don't really remember, but in one of the talks given by Paddy, sir, he mentioned Bogoliubov transformation, and he did a specific transformation for I don't remember which metric, but it was something related to that only.
The
I
transformation
completely agree.
depends on the metric, but because Bogoliubov transformations are just moving from one canonical system to another canonical system.
Yeah.
Right?
Uh,
So it's a
so
transformation on coordinates, and I don't understand what you mean by a transformation on the metric. So
yeah, I'm sorry if I'm making any mistake. All that I want to say is that you can equate the creation and annihilation operators at the horizon with the creation and annihilation operators at the past and infinity. Uh, that the transformation which does so is called Bogoliubov transformation.
yeah, that's cool. Thank you. I'm sorry to
Yeah,
interrupt you. Go on.
I'm happy to answer. Okay, so if you compute the number operator of modes going outside the horizon, so I'm the modes in the Penrose diagram which are going outside the horizon. Uh, yeah, yeah. So yeah, so modes which go outside the horizon are labeled as BT. And if you compute the number operator for modes going outside the horizon with respect to the past infinity, you will find that this has a non-zero expectation value. And the precise form of the number operator is the summation of all frequency modes k prime over the Bogoliubov coefficients. And you can find the explicit form for the number operator which Hawking did. And I'm not going through the exact derivation, but what it suggests is that in the Schwarzschild spacetime, assuming semi-classical gravity to be valid, there is some kind of particle creation uh, happening because the number operator for the outgoing modes is non-zero. Now, and interestingly, the spectrum of the number operator is exactly like the black body spectrum. And the so h bar omega is the energy of the outgoing modes since these are free harmonic oscillators. And you will find that each of these modes have a characteristic temperature called Hawking temperature. And what the picture seems to suggest is that after scattering through the horizon of black hole, there is some spontaneous creation of particles. And these particles seem to follow the black body spectrum. And since each particle has a black body spectrum, it seems like it doesn't carry information about the initial state of the incoming wave or of the yeah, it doesn't seem to carry information about the initial state of the incoming wave. We can visualize this particle creation process more efficiently pictorially. So it's a I don't know why it's yeah. So it's a feature of quantum field theory that there are spontaneous creation of particle-antiparticle pairs in vacuum. And suppose you consider one such particle-antiparticle pair close to the horizon of a black hole. Uh, Now, both the particles would tend to register enormous amount of tidal force, but the particle nearby would tend to have much more gravitational force, which would cause it to be engulfed by the black hole. And due to the conservation of energy and momentum, you will find that the other particle has to go outwards. This outgoing particle is called the Hawking particle, and it follows the black body spectrum which we just computed. So the interesting thing about the Hawking particle is that each particle follows the black body spectrum. It's not like the collective statistics of a number of particles follows the black body spectrum, so that you can decode the information about the initial state by measuring tiny correlations of each particle. It seems to be like the information about the initial state of the system is lost because the black body spectrum is universal and doesn't know anything about the initial state of the system. Is this point clear?
Yeah.
Yeah, okay. Thank you. Okay, so this gives us the spectrum gives us the famous temperature called the Hawking temperature, which you will find to be enormously small for most of the black holes that we observe in our galaxy. So this temperature is given as 6 into 10 raised to power 8 ms by ms m. So ms here is the solar mass, and since most of the black holes are much more massive than uh, than the mass of sun, it's an enormously small temperature. But the interesting point which Hawking temperature seems to suggest is that since black holes can radiate, they are not like completely black objects. Uh, they tend to behave like thermodynamical objects and carry entropy and temperature. And since they carry entropy and temperature, they must follow the laws of thermodynamics. So it seems like the analogy we proposed between the laws of black hole mechanics and the laws of thermodynamics appears somewhat real. Okay, so and since black holes are radiating like a black body, we can assume that black holes radiate obeying the Stephen Boltzmann law. That is, the power radiated by a black hole is given as sigma 84, which can be written as dm by dt into c square. I've removed c for simplicity. So you find that the energy radiated by the power radiated by black hole varies. Okay, I made some mistake here. Yeah. So since P is sigma 84, and you know that area of a black hole is scales with R square, and R is proportional to M, and T is inversely proportional to M. So T is inversely proportional to M. So the power radiated by a black hole varies as 1 by M square. So in the initial stages of black hole evaporation, uh, the rate of emission of Hawking radiation would be very small. So you can assume it to be almost like a quasi-static process where the changes between the system, which is the black hole, and the surrounding, which involves the exchange of Hawking radiation, is infinitesimally small. And if you compute the lifetime of black hole using this formula, you'll find that the lifetime of black holes, most of the black holes in our galaxy is much larger than the present age of universe. So it seems very difficult to detect Hawking radiation experimentally. However, at late times, the rate of emission of Hawking radiation would be very rapid and would be dominated by quantum effects. So, okay, I'm not getting into that. You can represent the, yeah, I'm sorry. Since black hole is evaporating, you can assume that the initial black hole would eventually evaporate. So if you represent it using the Penrose diagram, it would appear that all the interior of the black hole along with the singularity has disappeared, and at at very late times, the Penrose diagram for a black hole is identical to the Penrose diagram for a flat spacetime. Is this point clear?
Yes, go on.
Yeah, thank you. Okay, so since black holes have analogy with the laws of thermodynamics, uh, we can frame a first law of thermodynamics. T delta S is equal to delta U plus P delta V. So delta S is the change in the entropy of a black hole, and so we are assuming that the classical picture of black hole is not valid. And if you assume quantum mechanics, black holes tend to carry entropy and temperature, and you are considering some thermodynamic process which changes the entropy by an infinitesimal amount delta S, and this is equal to the change in the internal energy plus the P delta V term. Now, since first child solutions are vacuum solutions to Einstein gravity, there is no mass, no stress energy tensor, hence no pressure in the system. So you can rewrite the first law as delta S is equal to delta U upon T. So, or so just a minute. Yeah, assuming the evaporation process is quasi-static, you can assume that the temperature of the Hawking radiation is almost constant. So you can integrate delta S over a finite interval, or you can simply say that the entropy of a I'm really sorry for this, that the entropy of a black hole is U by T, where U is the energy of the black hole. And since U is equal to mc square and 1 by T scales as m, so you find that the entropy of a black hole scales as m square, which is like r square. So the entropy of a black hole scales with its area, as was proposed by Bekenstein much earlier and eventually verified by Hawking. Now, the exact form of the entropy of a black hole is this, which can be written using Planck's length as a by 4 Lp square. For a solar mass black hole, this is an enormously large number and is much, much greater than the entropy of star. So it seems to suggest that, okay, so a microscopic theory of gravity must account for such a large entropy. If the entropy of a astronomical object like our sun is around 10 raised to power 29 or 30. Uh, if you want, I can, meaning I'm assuming the entropy to be a thermodynamic process so that you can rewrite the entropy of star as U by T, and you can evaluate the temperature of the emitted radiation from the star, and you can compute the mass of the solar mass of black hole, and you can compute its entropy. So it suggests that black holes carry much larger entropy than the entropy of most of the objects, astronomical objects in our galaxy. So the interesting property of the entropy of a black hole is that it scales with area. However, the thermodynamical entropy is defined as a kV log W, where W are the microstates of spacetime. Uh, you all know that we define W to be the volume of phase space. So it seems like there is no phase space of a black hole, or the definition of entropy of a black hole requires a dramatic revision in our concept and definitions of entropy. So either there do not exist phase space of black hole, that is, black holes have no interior, space-time seems to end abruptly at the horizon, and all the entropy is stored at the horizon of black hole. Or the other viewpoint is that the phase space of black hole can be described entirely using only the boundary data. Thus, the interior and horizon of black hole seem to describe the same physics, which is called the holography, which is the famous idea of holography, which okay, I won't go into that. I'm audible. No, I don't seem to be getting any response, so it's
No,
just
no, you're audible.
Does anyone have any question?
Yeah, Shreyansh, can you hear me?
Yeah, yeah.
Yeah, so just on the previous slide, could you elaborate slightly about what you mean with the question, where is the phase space of the black hole?
Yeah, so if you assume the definition that entropy is given as the log of volume of phase space,
Hmm?
now seems since black hole entropy is proportional only to area, there isn't any phase space of a black hole. Meaning all the data of the entropy of a black hole is at the horizon. Is
Oh,
this point clear? Okay,
Um,
so now there are two possibilities that either black holes have no interior or that you can describe the bulk spacetime exactly using the boundary data. So whether you include the phase space or you count the entropy just by considering the entropy at the horizon, it doesn't matter. So it's like the idea of holography.
so you could do a calculation like a surface
Uh,
integral and like with with just the information on the surface, and you wouldn't miss out on anything.
Yeah, yeah. So I'm just making this. Uh, we don't have a meaning. I don't know of any precise calculation of how to compute the entropy of a black hole from some microscopic theory. But the proposal that the entropy scales with area seems to suggest these two possibilities.
Mm, uh, Sorry, just one other
Yeah,
question, which is um, could, I just don't see the connection how it being proportional to area would imply that. Okay, so you're saying it's okay. I think I sort of get it. You can continue. Sorry.
yeah. Thank you. So, okay, so we can next consider the second law of thermodynamics. So suppose we have a black hole with some with some matter. I'm sorry, can I just take a minute? I'm just coming in a minute. I just wanted to drink some water.
Devanshu, about the thing that I mentioned, I got confused between the Rindler transformation and the Boglevo one. I had done
Ah,
it
I
like a,
see. I see. I see. Yeah.
I mean, Paddy sir had given a lecture last summer on QFT and GR, so that time I was just learning about all that, so I think I got confused between those two.
No worries. It's all right.
Okay, so we can next consider the second law of thermodynamics. So suppose we have a black hole and some matter. This matter tends to fall inside the black hole. In the initial stages, since the black hole evaporation is a quasi-static process, you can assume that the matter tends to have been a part of black hole, and there is no emission of Hawking radiation. Now, the validity of the laws of thermodynamics indicate that the change in entropy must be greater than zero. Now, the change in the black hole entropy scales as area, or the change in the area. So the second law of thermodynamics suggests that the change in the area is greater than the entropy carried by the matter. Okay, so it suggests that black holes seem to carry more entropy than any other thermodynamical object. An analogy to see this is suppose we consider a system of ideal gas with some entropy, And one considers a process to increase the entropy indefinitely by adding more and more ideal gas in the system. What would eventually happen is that the system would tend to collapse and form a black hole with an event horizon, and the entropy would then scale with the area. Does it suggest that black holes are like thermodynamical objects with maximum entropy, and entropy of a thermodynamical object cannot grow more than its area, rather than the volume of the rather than volume, which would appear to be the more intuitive picture. So black holes seem to be objects containing the maximum entropy. This is called the maximum entropy bound. Now, Hawking radiation seems to be in conflict with unitarity in quantum mechanics. As since we know that Hawking radiation has a black body spectrum, uh, unlike black body radiation, where the statistics of all particles follow the black body spectrum, it is like each Hawking particle has a black body spectrum and doesn't seem to know information about the initial pure state of black hole from which it was formed. So what I'm trying to say is that as the black hole evaporates, the outgoing Hawking radiation is in thermal state. But assuming semi-classical gravity, you can phrase that the black hole is made of some pure state, which in the process of evaporation has turned into a thermal state. So if you scale the entropy of the whole process with time, the initial entropy was zero, and it just continues going up with time uh, in the process of Hawking radiation, and would tend to saturate at some value when the black hole has evaporated completely. So this seems to be in contradiction with the principles of quantum mechanics that a pure state must eventually evolve into a pure state. Uh, so now, when we propose some arguments to resolve the information paradox, when we say that Hawking's calculation is semi-classical, meaning you don't quantize the gravity entirely, you assume it to be classical, and quantize matter field. So maybe Hawking's calculation is not exact to, to meaning it's not too
Hello,
yet exact.
hello, Bhaiya.
Uh-huh.
Can you please explain
Yeah.
the paradox again?
Okay. Okay. Uh, okay. So okay. Yeah. Yeah, I'm sorry. When you consider a black body, you find that the spectrum of black body is thermal. So it seems to suggest that the information about the object which is emitting the radiation is lost.
Yeah.
But it's not it's the statistics of a collection of very large number of particles which obeys the Bose-Einstein statistics. But if you measure the correlations of individual particles, you will find that each individual particle carries more additional information, but the complete statistic has a black body spectrum. But in the case of Hawking radiation, you find that each Hawking particle has a black body spectrum, and the since the outgoing radiation is thermal, you will find that the complete evaporation of black hole uh, suggests that the entropy of a system which was initially at pure state, this is the variation of entropy with time. This is the entropy. So pure state evolves to a thermal state, and this is in conflict with the principles of quantum mechanics that a pure state can't evolve to a mixed state.
Okay, Bhaiya.
Is
Got it.
so I need to review the proposals for yeah. So Hawking effect one may argue that Hawking effect is semi-classical, so small corrections to Hawking radiation can restore unitarity, uh, meaning a complete theory of gravity may contain Hawking radiation, which is not exactly thermal, but has some signature of some information about the initial state from which the radiation was emitted. Uh, these effects may come from Planckian or quantum effects. Now, another interesting argument is that as we know that the rate of emission of Hawking radiation, that is the power of emission of Hawking radiation, scales as 1 by m square. So, at very late times, when the black hole has evaporated significantly, uh, the rate of emission of Hawking radiation would be very large. So, uh, since the rate of emission is very large, this can deform the geometry of the horizon. So, we don't know how the Hawking, meaning the spectrum of Hawking radiation, when the quasi-static limit of the emission of Hawking radiation is violated. Meaning we cannot assume that semi-classical gravity is valid when black hole has evaporated significantly. So maybe those effects can resolve the information paradox. Maybe the late-going Hawking radiation seems to carry information about the initial state, and the complete Hawking radiation is not exactly thermal. So that is called the back reaction effect, meaning the Hawking radiation deforms the metric at late times, so that the geometry cannot be exactly assumed to be semi-classical. And and the late time Hawking radiation seems to purify the early Hawking radiation, which restores unitarity in the theory. Okay, so what this proposal seems to suggest is that a consistent theory of gravity must describe the process of formation and evaporation of a black hole as a unitary process. So, by unitary, I mean that there should be some kind of scattering matrix or S matrix in the theory, which relates exactly the incoming states, that is, the states which were at past null infinity. Uh, uh, I hope you all remember the incoming states and the outgoing states. And the exact evaporation should not be a thermal process. And the physics outside a black hole is approximated by semi-classical gravity, meaning you can assume the assumption made by Hawking that geometry near the horizon is classical, and quantize the matter fields in that space-time. And the third assumption is the smoothness of the horizon. That is, any infalling observer would not find uh, anything special at the horizon. So, what is smoothness of the horizon? So, smoothness of horizon comes from the equivalence principle. So, Einstein's equivalence principle suggests that physics observed in different frame of references are equivalent, meaning whether you are an infalling observer or an observer at a very large distance, say infinity, there is always some coordinate transformation which relates the two set of observers. Uh, so the horizon would be described as good by an infalling observer as by an observer very far away from the horizon. Now the smoothness of horizon implies that if you compute the entanglement entropy of region A and B, uh, then it's zero. Is this statement, meaning I know that I need to make it precise, but I hope you all are familiar with how we define entanglement entropy.
No, I'm not familiar. Could you go into that?
Uh, you must be knowing how to define entanglement entropy. Okay, I need to review it. Uh, okay, so it's some measure of the degree of correlation between two systems A and B. And if a system, if the composite system AB is in pure state, then the entanglement entropy is zero, since a pure state has no correlation. And now the equivalence principle suggests that the horizon should be a smooth place. I will go through uh, why it should be the case in the next slide. But yeah, so is this point here, meaning the entanglement entropy should of the region A? A is the interior of black hole, and B is the region just outside the horizon. Meaning,
Yeah.
yeah, so entanglement entropy of AB is zero. That ensures the smoothness of the horizon. Otherwise, if the entanglement entropy is non-zero, then the composite system is not in a pure state, or it's not in the vacuum state. So since the entanglement entropy is non-zero,
Hello.
this
Your voice is not clear. I think can you put your phone closer, I guess?
okay,
Yes, it's well.
just a minute. So if entanglement entropy is non-zero, you would register particles at the horizon. The registering of particle is in conflict with the smoothness of horizon, and which violates equivalence principle. Okay. Okay, so I'm I'm making a slight detour from this.
Yeah. Hello. Shreyansh.
Uh,
What if we purposely take up an entangled set of system and like send one as an infalling observer and the other one just keeping outside?
yeah,
So I mean, how would that fit in with all this? Like, it's not the same as this. I mean, it's a different scenario. But what if we have a purely entangled set of state, and one of them is said incident into the black hole, and the other is just kept outside? Like, how would the measurement be affected? Or
one of them is uh,
what I'm saying
I
is,
wasn't able
if there
to
is an
hear you.
entangle,
No,
yeah, if there is an
uncertain.
entangle.
All I'm assuming is that suppose you have two observers outside the horizon. Now, Einstein's theory suggests that no two observers have, meaning all observers are related by coordinate transformation. In special relativity, you know that these transformations are Lorentz transformation. In general relativity, we modify this assumption and assume that an infalling observer just outside the horizon is as good as a observer far away. So the physics seen by the two observer is identical. So an observer, since a far away observer doesn't seem to register particles, since it's in the vacuum state, it shouldn't be that the infalling observer register particles. Does that clarify your point?
No, yeah, I got that. I was just asking something else. Okay, I'll ask that at the end. I mean, it's a completely different scenario.
Yeah. So assuming the Hawking radiation to be a unitary process, there should be some mechanism by which the Hawking radiation gets purified after a certain time. So suppose you draw the variation of the entropy of Hawking radiation with time. Initially, it seems to increase linearly, but after a certain time, called phase time, the entropy should tend to decrease. And since the whole process is unitary, the pure state must evolve to pure state. The final entanglement entropy should be zero. This curve should be should come from a consistent theory of gravity, which assumes Hawking's calculation is not a paradox, meaning it can remedy the Hawking calculation. Should be able to give the page curve. Is this clear?
Yeah.
Okay. Okay. So as a meaning the Hawking radiation after the page time should purify the early Hawking radiation uh, in a consistent theory of gravity. Okay, so these were called the old information paradox, meaning the versions of information paradox which were formulated by Hawking. But there are also recent versions of information paradox, which seems to suggest that Hawking's that the proposal that okay, that the proposal that semi-classical gravity with small corrections to Hawking effect can resolve the information paradox is wrong, meaning you find an order one correction to the information paradox. I will specify what that means. Okay, so we'll now try to formulate the recent versions of the information paradox. The first is the no cloning paradox, which was proposed by Samir Mathur in 2009. So, as meaning we are describing the space-time using the Penrose diagram, and we are assuming the whole process is unitary. Uh, so we are decomposing the space-time into some set of Cauchy slices, which is labeled by blue, and this purple line here is the infalling matter. So suppose we consider some Cauchy slice B. This Cauchy slice contains the infalling matter, which was responsible for the collapse and the formation of black hole, and it also seems to contain the some part of the outgoing Hawking radiation. Now, if you assume that Hawking evaporation process is unitary, there should be some mechanism in a consistent theory of gravity which is able to relate the uh, initial information about the infalling matter with the Hawking radiation. Is this point clear? Now, this seems to be in violation with the no cloning paradox, in that you are duplicating a quantum information in a Cauchy slice at points h and v. So it seems to suggest that there is something something wrong with the proposal, meaning there seems to be an order one paradox, meaning there should be some uh, something different, something coming from elsewhere which would tend to resolve the information paradox. It's not like small corrections to Hawking effect could resolve it. Uh, is this point clear? Uh, okay.
Yes.
Okay. So I'm now considering the second version of the information paradox, which is the firewall paradox. Before moving to it, I need to consider some properties of entanglement entropy. So I'm sorry I haven't defined what entanglement entropy is in this slides, but you can assume it to be some measure of the correlation between two entangled systems. So suppose we have three systems A, B, and C, and we denote the entanglement entropy of region A as SA. Now, the entanglement entropy seems to follow three set of laws, uh, which are the strong subarachidity law, which states that the entanglement entropy of composite system ABC plus entanglement entropy of system B is less than or equal to entanglement entropy of AB plus BC. Similarly, there is subadditivity law and Araki-Lane inequality. We will be using the three inequalities to give the firewall paradox. which is the paradox in the violation of these set of inequalities. Okay, so I'm reviewing the assumptions of a consistent theory of gravity again. Uh, as reviewed, the process and formation of black hole is unitary. Physics outside black hole is semi-classical. An infalling observer finds nothing special at the horizon. And what will meaning horizon is a smooth place. What we will eventually find is that these set of assumptions are inconsistent with each other. Okay, so we label the three systems A, B, C for this setup as the interior of black hole, B as the region outside, which contains the outgoing Hawking radiation, and C is the future null infinity. So, okay, I hope meaning uh, future null infinity is the region where all of the Hawking radiation would tend to be collected at infinity. Uh, so if I want to represent it using Penrose diagram, this would be the future null infinity. This is the system A. This whole is the system B, and this is the system C. Uh, Now, if you assume that horizon is smooth, uh, meaning system, so this is system B and this is system C. If the composite system is smooth, then the entanglement entropy of VC is zero, and by strong subadditivity law, SABC is less than equal to SA since SBC is zero. From Araki-Leib inequality, we know that if we partition ABC into systems A and BC, then SABC is greater than equal to this. So the two inequalities suggest that the entanglement entropy of ABC is equal to the entanglement entropy of A. Now, if we use strong subadditivity law again, but this time consider systems AB and BC, then we have the equation 7, which is this. Now, since SABC is equal to SX, this suggests that SA plus SB is less than equal to SAB. Now, we know the subadditivity law that SA plus SB is greater than equal to SAB. And from equation sorry, from this equation, it seems to be violating the subadditivity law. So it seems to suggest that there is another version of information paradox, which is the violation of the subadditivity law. Uh, I mean, was I able to present it correctly, clearly? I, I'm not able to see the messages. Okay, okay. Which is completely containing information. Okay, so there is a question asked by me that why would the Hawking radiation, which is completely independent of the infalling particle, contain any information of that particle? So that's what the calculation of Hawking radiation suggests, but it seems to give a paradox that the outgoing Hawking radiation is thermal, which violates the principles of quantum mechanics. Uh, does that point clarify your doubt? Uh,
No, like my question was key that Hawking radiation is just because of the antiparticle getting
yeah.
into the sucked into the black hole, and then the particle released is the Hawking radiation. So how is that related to the infalling particle? As in, how why would it contain the same amount of energy information as the infalling particle or any
Uh,
particle respect actually?
so what? what Hawking radiation seems to be doing is that it tends to be evaporating the black hole by formation of particle-antiparticle pairs. Uh, Now, the initial, if you assume semi-classical gravity, then the initial black hole could be assumed to be in some pure state. But the final Hawking radiation seems to be in thermal state. No, I'm not saying that Hawking radiation should contain any information about the black hole, but for the theory to be consistent with quantum mechanics, Hawking radiation, meaning the mechanism by which Hawking radiation is evaporating, doesn't seem to carry any information about the interior of black hole. But some there should be some mechanism in a consistent theory of gravity, which is able to uh, mimic pure state to pure state eventually. But this doesn't seem to be so. So, does that answer your question? Uh,
Yeah, okay. Yeah.
okay, so having reviewed the strong subadditivity paradox, uh, I hope you have you meaning
Hello.
uh, is my voice audible?
Yeah. Yes, sir.
Okay. Okay. So suppose we consider the evaporation of black hole after the phase time, then the system B tends to purify A. Uh, so the entanglement entropy of AB is less than SA since B is purifying A. So the composite system has smaller entanglement entropy than the system A. From this, if we consider this equation again, since SAB is less than SA, we find that SB is less than equal to 0. But since the outgoing radiation is thermal, SB must be greater than 0. Uh, so it seems like the assumption for the smoothness of horizon, which comes from the equivalence principle and unitarity of quantum mechanics, seem to be in conflict. Okay, so what the four authors AMPS did was they found the strong subadditivity paradox and they modified the assumption for the smoothness of horizon. That is, horizon was not assumed to be a smooth place, as should be from the Einstein's equivalence principle. Uh, they found that if you remove the smoothness of horizon, you will find that you eventually okay. So this leads to firewall paradox, meaning if you do not assume the smoothness of horizon, you find a firewall paradox. Now, I'm just planning to review how the smoothness of horizon leads to firewall paradox, meaning the non-smoothness of horizon. So it's a feature of any quantum field theory that there is high degree of entanglement between any region and its complement. So suppose we consider a space-time which is partitioned at the origin into left and right region, then you can find that it's a feature of quantum field theory that there is high degree of entanglement between regions L and R, and in order to so this was the assumption that no, okay, it's just getting a bit. So suppose we consider Rindler space. into two regions L and R, then there is high degree of entanglement between regions L and R, and there is high degree of entanglement between region L and R in order to ensure that space-time can be smoothly extended from R to L. Now, if you want to remove this smoothness, you need to break the entanglement between left and right region. And to remove this entanglement between regions L and R, you need to supply very high or infinite amount of energy. And the supply of this infinite amount of energy ends the space-time at the origin, meaning if you want to break the entanglement between L and R, you need to supply infinite energy at the origin. And this infinite supply of energy would tend to end the space-time at the horizon itself. So it seems like if you want to remove the smoothness between region in the interior and the exterior, you need to supply infinite amount of energy at the horizon, which would generate a firewall at the horizon, and the space-time would end up abruptly at the horizon. This is really a strange conclusion, which seems to come from which seems to come assuming the validity of smoothness of the horizon, which comes from equivalence principle and quantum information inequalities. So these are called the recent or the modern versions of the information paradox. Now there are two cousins of information paradox: the occupancy paradox and any not equal to zero. I won't go through these paradoxes, uh, but these pictures seem to suggest that there should be some drastic modification in how we understand gravity and quantum mechanics in uh, around black holes. So much of the approach to address this problem has been using the ADS-CFT correspondence, which I won't be able to review here due to my ignorance and constraints. It has led to many new ideas related to information paradox. The two set of The two set of ideas I'm interested in knowing are state dependence and quantum error correction, which were proposed by Professor Surat and Kyriakos Papadimos. And quantum error correction was proposed by Ahmed Almiri, Daniel Harlow, and Shidong. Okay, so we do not yet have a very complete picture where we can address the old information paradox and the modern version of the information paradox. But from 2015, there has been a lot of interesting work in this regards. And last year in May, there were a number of interesting papers, which are too technical for me to understand by many authors, which seem to be able to resolve the information paradox and were able to calculate the page curve of Hawking radiation uh, by and were able to calculate the page curve of Hawking radiation. Uh, and these set of ideas seem to give many. These set of ideas seem to suggest how gravity works. Uh, thank you. Uh, you can ask questions if you like. If there was some point which was not clear, or
Guys, if you have any doubts, you can ask.
maybe I have messed up
Okay.
a few places. I don't know, but
Hmm.
I hope the picture is clear.
There's a
That
doubt
is,
in the chat.
okay. Uh, which slide should I? Okay, just. I mean, what is the doubt?
Are there any resolutions to the paradox, like information contained in a very small but finite space in a black hole?
You are talking about remnants. So, uh, what you are suggesting is that black hole doesn't evaporate completely, but there is high degree of entanglement between some region B and its complement. But since it so remnants are very small objects, meaning and the idea that they tend to contain very high degree of very high amount of entanglement entropy is not something we do know how to get through from a theory of gravity. Meaning, it's not a since Hawking calculation is not exactly has hasn't been exactly done, so we can't say whether there exist objects like remnants which seem to give resolution to information paradox by containing information in a small region. Uh, but there are other interesting routes. But there are other routes through which we can address this problem. Two set of yeah. So that's all I could say about it. Uh, does that clarify your question? Okay.
What
So
are
okay. Yeah. So other two routes are meaning there are many other routes, but two set of ideas which I'm interested in are state dependence and quantum error correction. So state dependence suggests that so suppose you have some state psi, and then you know that operators in quantum mechanics maps one state to some other state. But these operators are not uh, do not depend on state. So suppose you have some vector in Hilbert space. So you suppose some spin particle, and you do a Stern-Gerlach transformation, meaning you do some unitary on that. That rotates the spin axis of the particle. But the action of that unitary doesn't depend on the state of the spin state of the electron or some particle. Meaning you can perform the same unitary operation on different states and it will act the same way. But what state dependence suggests is that in order to describe consistently a theory of gravity, uh, you need uh, to yeah, I'm sorry. To describe the interior of black hole, you need operators which are state dependent, meaning if you choose some state, that operator would act in some way, but in some other different state, it would act differently. There is a lot of literature on state dependence, and it requires one or two more set of lectures to explain exactly what is state dependence. Uh, so I won't be able to explain you more precisely what state dependence is. The other idea is of quantum error correction. So you assume that ADS-CFT is valid. So for the consistency of information paradox, you require that the CFT should act like an error correcting code. And I have almost no knowledge about quantum error correction, so I won't be able to review that too. I have gone a bit through state dependence, but I won't be able to review it this at this time. So that's yeah, that's all I could say about your question. Okay, so uh, ADS-CFT seems to give a non-perturbative definition of how a theory of quantum gravity should look like. Meaning, we since I had already motivated that semi-classical that Hawking's calculation was semi-classical, and we yet do not have a we yet do not have a complete theory of gravity for d Sitter space. But however, in 1998, uh, the young scientist Maldacena found a beautiful theory in which he was able to relate a gravitational theory from using a non-gravitational theory, and it seemed to answer a number of questions which seemed to be not being able to addressed using other proposals. So ADS-CFT seems to be the most promising route to most of the people who try to understand gravity. Okay, so it can be the I don't know about that, Neil, so I won't be able to comment about it. I need to go through your question. I don't know about it, Neil. I need to think about it. Okay, so uh, Nick, I just want
Yeah, I
to.
think we can close it now.
I'm
Right.
sorry, it went.
And it's fine. It's good. It was nice talk. I have recorded it also. I'll share it with everyone.
Yeah, yeah, yeah. Thank you.